Now, in this section, I want to give you our very first step-by-step synthesis approach of our first realistic filter. So we're going to basically learn how to make a bandpass filter based on capacitive gaps that are going to be implementing our coupling sections. And this is really the approach that you have to follow for your design project. So that's the filter I have actually asked you to implement. So first of all, let me show you how the filter will look like. So there are going to be a bunch of transmission lines. So each one of these squares here shows the layout of a transmission line section. And here you can understand we're talking about a microstrip line. So this is essentially a top view of the filter. And the coupling of energy from one resonator to the next, it will actually be realized by bringing these transmission lines close to each other. So physically, we're going to implement the coupling sections by basically bringing the transmission lines close to each other. This is going to be our input transmission line right here. Let me actually use my green marker. So this will be my input transmission line, and this will be my output transmission line. And typically, the width of this will be such that this transmission line here is a 50 ohm impedance, because usually the input and the output will have to be 50 ohms. Now, it's not necessarily true that the width of these resonators must be the same number W. In fact, there are some good reasons why it should not be. For example, it turns out that the quality factor of these resonators, which is something we'll discuss more in detail later on, is actually a function of the impedance of these things. So often what happens is we optimize the impedance of these resonators such that we have the highest possible quality factor. But to keep things simple here, I will make the assumption that the resonator impedance here is also 50 ohms, and that means the W will be the same as the input and output. So given this assumption, which again often is suboptimal, now the question is the following. You have to find out the lengths of these transmission lines, so how long each one of these things should be, and the gaps. So these are basically the unknowns. And so the synthesis process that I will show you will answer exactly this question. Now, there are some tools we have at our disposal. The first tool we already know, but I want to remind you this, is basically the ABCD matrix of a transmission line section. It's the one we've seen actually in the very first part of the class. And the second thing we haven't actually seen so much, but I do want to show you essentially why a transmission line section can actually be used as a resonator. So we have touched a little bit on this, but here's a quick reminder. So here's a transmission line. It can be microstrip, CPW, anything you want. If you actually short it and you look at the impedance at the input, you can use the equation we have derived before for any transmission line impedance, and it's the one right here. Now, if you look at this equation and you basically plot the tangent beta L, or the absolute value of the impedance, you will basically get the curve that you see right here. And so there are basically certain resonances that exist. For example, this transmission line section has a resonance at pi by 2. That means at electrical length of 90 degrees. Has a resonance at pi, and so on and so forth, 3 pi by 2 and so on. So practically, you can use this to realize a resonator at any of these resonant points. But what does change is the type of resonator that you will have. For example, if you use this sorted transmission line and you realize it when its electrical length is 90 degrees, the equivalent circuit, as is very clear from here, is going to be just a shunt LC. If on the other hand you choose to use this transmission line when its electrical length is 180 degrees, then its equivalent circuit around resonance will just be a series LC. Notice, by the way, something else that this graph shows us, which we have also seen before, which is that when the frequency is pretty low, meaning when you're here, way below resonance, this guy is a sorted transmission line. Let me say it again, is a sorted transmission line, which basically is equivalent to a j omega L, approximately, as an inductor. And we've actually talked about how you can implement inductors with short transmission lines. So basically, for this region here, you're having an equivalent circuit, which is just an inductance, while once you move the first resonance, past the first resonance, you have an equivalent circuit that's basically just a capacitance. Exactly the same thing holds for open circuit transmission lines. So if you just look at the impedance now, or the admittance rather, you will get this number. And so that means that at pi by 2, you will basically end up having an approximate series LC, again, just around resonance. At pi, you will get a shunt LC, just around resonance, and so on. So the layout I gave you for the filter implementation was something that looked like this. So open transmission line sections coupled with each other. So essentially, the picture you should have in mind is this one right here. So we will have open transmission line sections. And now we have to basically choose what resonance we're going to realize, or at least we're going to use. So it turns out that I'm going to go with implementation. We're going to keep our shunt components from the very first filter. And so that means I want this. So because my realization will be a coupling section, which again will be done from the gap, and I'll explain more about this. And then I want a shunt LC, and then another coupler, and another shunt LC. Now, in the next lecture, I'm going to show you, in case you're wondering, why we're using a transmission line to implement these LCs. Why we're not using, for example, shunt real L and real C, and why we have to make this approximation. The preview of the answer is that there are certain frequencies where you cannot use LC. For example, if this is supposed to be a 50 gigahertz filter, there's no way you can build a good inductor at 50 gigahertz. Or if this filter was, let's say, synthesized in the optical domain, good luck in building an optical inductor. You can't do that. So it really has to do with the frequency range that you're basically using. So to summarize from this discussion, we're going to basically be using open transmission line sections around pi, around basically 180 degrees, the second resonance of this, to basically get an equivalent LC. Just one more warning. Once you move far away from this, the system of course behavior is destroyed because the transmission line sections don't do what you want them to do. And I also want to make a few comments for the physical realization we're talking about here. So we're going to basically be using microstrip line, but a slightly more advanced version of a microstrip line, which is called a suspended substrate strip line. So what's happening in this case is that normally you would use the entire substrate here. So you would have basically a piece of metal on a substrate. Well, that's a bad idea if you want high quality factor, because this guy here will have some type of a loss tangent, some type of a dielectric loss. So to get rid of this dielectric loss, we basically etch the substrate away, or we machine it down to a very small thickness, just enough to mechanically support our circuit. And so now basically the dielectric loss is completely gone from the equation, and the only loss we have to worry about is the ohmic loss of this. And often there is a package for this system. So I have actually indicated this package right here. So there's going to be a box, essentially a metallic box, whose thickness will be H, and of course the width will be A to house this line. It doesn't mean that this is the only implementation, but I do want to give you a physical image of how this thing will look like when we make it. Now let's talk about the gap. So for the transmission line section that I just showed you, the suspended strip line, there is a pretty interesting and pretty accurate equivalent circuit for this gap here. As you can imagine, this gap is nothing else but a capacitor. That's the most physically intuitive feeling that comes. But in addition to this intuitive understood capacitance, because you're having fringing fields coupled from one to the next, you also have these two shunt capacitances, which are reasonable again because you have some substrate and some ground plane. And so this equivalent circuit that you see right there is actually pretty simple, and it would apply, I would say, to any type of a gap-based coupling. But these equations here apply basically for the particular physical realization of the suspended strip line. So these equations, for example, you can see that the susceptance BA, which is basically the susceptance of this capacitor right here, is a function of your H, this is the height of the package, is a function of lambda G, that's the guided wavelength, is a function of S, which is the space. And similar equations apply for the B sub B. So when we synthesize the filter, the approach we're going to take is we will basically strive to find these numbers. Essentially, that means the CA and the CB. And once we know those numbers, we're going to use these equations in the reverse mode to basically find the gap S. Right? That's basically what it's going to be. The S is really the unknown, the physical implementation unknown, while H will be constant. Lastly, this equation here gives you the ABCD matrix of this pi network, which again we have seen before. So this is a reminder, and also the explicit expressions I promised you in the previous section regarding the J inverters and the shunt elements. So these are the expressions that basically we have derived before. And what happens here is because we need to start from here and synthesize a bandpass filter, we will replace this C with an LC, the shunt LC, like we discussed before. So this is the mapping that we basically already have introduced. And if you basically do all of these calculations, you will end up having the equations that you see right here. For example, the J01, which is the first coupling section between the source and the first resonator. Here's the first resonator that, as we have already discussed, this will be an open transmission line. Depends on delta omega, the absolute bandwidth, the admittance of the source, this arbitrary number C1 prime, and then the G naught and G1. These are the G parameters of the filters that you need to implement. And the same thing holds everywhere else. So here's the goal now. Once again, stated slightly more explicitly, we're going to basically associate the resonators with the transmission lines. I already explained why we did that. We're going to associate the inverters with a gap. And our goal now is to basically find the value we need for the physical implementation once we know all of these J inverters from the system. But there is a problem. The problem is that if you look at the equations we have right here, they are talking about these capacitance values. The problem is that, as we just discussed, we're not going to have physical capacitances. This guy here will have just a transmission line. Similarly, this one here will just be a transmission line. So how do I go from this idea that I have already discussed, finding the J inverters when I have a real physical capacitance, to finding the J inverters when I basically have nothing else but a piece of metal? Well, the way we actually do this is we take a little bit of a detour, and instead of talking about the resonator equivalent L and C, we actually talk about the resonator susceptance. So our goal will be, and this is something that we will complete next time, our goal will be to link this resonator susceptance to basically the physical realization of my resonator, and replace the numbers that you see here, the C and the C prime, with this resonator susceptance. So what we're going to do is we're going to very quickly rederive the equations that you see here, but not for C's, but for the resonator susceptance. And to be slightly more explicit, we're not going to rederive them for this capital B, but rather with a normalized derivative at resonance. And that's because it's very simple to do.